Welcome to the Automotive Diagnostic Podcast. We're going to explore ways to sharpen our diagnostic skills, find learning resources, and hear from experts in the automotive field. Okay, welcome to the Automotive Diagnostic Podcast. Thank you for joining me today. My name is Sean Tipping. I am the host of the Automotive Diagnostic Podcast. We're going to be starting what is going to be a three-part series. Today will be part one, obviously, and what I want to talk about is how engine computers for a vehicle measure or calculate the incoming air mass to the engine. The computer needs to know how much air is going into the engine so it can add the proper amount of fuel. Now, there's other things that go into the fuel calculations, such as RPM and throttle position, engine temperature, many other things that go into that calculation. But one of the most important for adding the correct amount of fuel is knowing the correct amount of air. If we don't know how much air is going into the engine, how many oxygen molecules are entering each cylinder as the engine's running, we can't add the proper amount of fuel. And the challenge of the engine computer, a PCM, I use PCM a lot, powertrain control module, so you may hear me use that acronym. By that I mean engine computer. I know there's many other names depending on the manufacturer, but I'll probably say PCM just to shorten it up. One of the goals of the PCM, the challenges of the PCM, is that it can add a precise amount of fuel, given that everything's working correctly, fuel pressure, injectors, all that stuff on the fuel side of things. It has precise control via pulse width modulation of a fuel injector, and it can add as little or as much fuel as it needs to. But getting the proper amount of air, getting a precise amount of air into the engine, into the cylinders, into the intake manifold, it's not quite an exact science, and it's going to change all the time depending on throttle position, engine load, and engine speed. So we need a sensor, we need a calculation, a way to determine how much air is going in so we can add the correct amount of fuel. And so that's what I want to talk about, is the different ways that engine computers do this. So the 3 episodes I'm going to put out on this, one of them is going to be today mass airflow sensors. It's one way that we calculate incoming air mass. The second part is actually going to be a method that we use to test mass airflow sensors, known as volumetric efficiency testing. And it has some other purposes too, but I like to use it for mass airflow sensor testing. It works really well. And then the third part of this will be on speed density systems that do not use a mass airflow sensor and use manifold absolute pressure sensors as their main input for this calculation. And in that episode, we'll describe some differences between mass airflow and speed density systems. So that's what we're going to have. Let's get into it right away. We're going to talk about airflow sensors or mass airflow sensors today. Mass airflow is the term. We shorten that up to MAF, M-A-F. So I'll try to say mass airflow as much as I can, because here's the deal. When we talk about MAP, M-A-P, and MAF, M-A-F, sometimes you can misunderstand what someone is saying when they just say MAP or MAF. So I'll try to say mass airflow as much as I can. I may shorten it up to MAF sensor, and I'll try to be as clear as I can on that. But again, this is our airflow sensor. We do see airflow sensors used in a couple other areas in the vehicle, but not as frequently. You can see them in air injection systems and a couple other areas of the vehicle, but our most common place that we're going to see an airflow sensor is used with the engine computer with the fuel injection system. This is a major input for fuel delivery and for ignition timing as well, just for the PCM to calculate engine load. How much air do we have going into that engine? If you're not familiar, an engine is just a big air pump, okay? We take the air in, we're going to have our intake stroke, we're going to squeeze that air, we're going to have a power stroke, and then we push that air out. It's a breathing apparatus, pulling air in, pushing air out. And the amount of air that we're pulling in is what we need to add fuel to in order to have our 4-stroke event. So this sensor's there to tell the computer how much air did go into this engine at any given point, because obviously that airflow is going to change as engine speed and engine load change throughout the operation of the vehicle. If you want to think of it this way, it's really just a kind of a math equation if you break it down to the simplest level. And in reality, if you get into it, it's not exactly simple, but I like to simplify things so I can understand them, so I can wrap my head around them. Makes it easier for me when I'm thinking about the components. But if we just think about our two main components going into the combustion process, we have hydrocarbons, which is fuel, gasoline going into that engine, or heck, you could say diesel or whatever fuel you're running your engine on, but I work mostly on gas engines, so our hydrocarbons, our gasoline is what we're talking about there. That's one component that's going in. And then we have oxygen, which is 21% of the air that's going into the cylinder. Those are our two big players in this math equation. Now, there's also 78% nitrogen that's used to actually expand from the heat of combustion, push the piston down. Not exactly what we're focusing on today, the 4-stroke cycle. I'm sure many of you are familiar with that. But what I'm focusing on here is that the amount of hydrocarbons to oxygen has to be at the right level. So, or they have to be at the right levels going into the combustion process when we have the intake stroke in order to get the desired product out. Now, what we're really after is the heat energy in the fuel source, in those hydrocarbons. When we break those hydrocarbon chains, separate the hydrogen and carbon, and bond them with the oxygen molecules, we create water vapor and we create carbon dioxide. Yeah, that's the goal, but what we're getting out of it is heat energy, and that's what's really pushing the piston down. But for that to happen, our hydrocarbon levels and our oxygen levels need to be correct. If we talk about stoichiometric being the ratio between air and fuel going into an engine, all right? So really, this is just a math equation that the PCM's trying to figure out. Well, it has the calculation, and again, it can precisely add the right amount of fuel to this equation, the hydrocarbons. The question mark is how much air came in first. How much air did we draw into that engine? That is going to allow the PCM to figure out, I need to add this much fuel so that we have our stoichiometric mixture, or depending on the scenario, maybe we're accelerating wide open throttle and we're going to go into a rich condition, whatever that might be, but it is trying to add the correct amount of fuel. That's the goal, and this sensor is what is allowing us to figure out that equation. So we're going to go over some basics of the sensor, our mass airflow sensor. Some of this you may be very familiar with, maybe you're not, but we're going to go over basics and then we'll get into some more of the details on the sensor. So first things first, not every vehicle uses a mass airflow, and this is one of the reasons that I'm doing this series, is that I see a lot of people that don't necessarily understand. One of the first things, if I'm dealing with a fuel trim issue or a fuel related code, let's say I get a P0171 or 174 or lean or a rich code, the first thing I want to know is, how's the fuel control work on this? Does this vehicle have a mass airflow sensor, or is it speed density? So being able to identify that is going to be your first step. And if you're familiar with the vehicle, you probably already know, but maybe you've never worked on this make or model, or maybe it's brand new and you need to figure out, what system does this use? Does it have a mass airflow or does it not? So first things first, not every vehicle does use a mass airflow, so you're going to want to identify it. The way to easily identify it, obviously you can check your service info, but you can also just look under the hood and you're going to look between the air filter housing and the throttle body. And generally there's a rubber tube of some sort, and somewhere either on the air filter housing, in that air duct between the throttle and the housing, or sometimes even on the throttle body, depending on the application, there's going to be mass airflow sensor. Now that sensor has to be between that air filter and that throttle. It can't be after the throttle. And by after the throttle, I would mean on the intake, the vacuum side of things. It can't be there. It has to be before the throttle. If you think of where intake manifold vacuum is, we're on the opposite side of that. That's where that mass airflow sensor is. If it was on the inside of the intake manifold, the turbulence of the air would not be correct for this sensor to read correctly. So it has to be before the throttle on the air filter side of the throttle, but it also has to be after the air filter because this is a sensitive sensor and any debris or anything that comes through can actually damage this sensor pretty easily, or at least create a dirty sensor, which we'll talk about later, the problems you can have there. So when we look at our typical mass airflow sensor, we're going to see 3 wires, power, ground, and signal. Some of these can be 5 volts and then have a signal wire and a ground. Now, you'll see a lot of sensors that have 5 wires. Keep in mind, a 5-wire mass airflow is actually including the air intake temperature sensor. So this is the sensor for the PCM that tells it what is the temperature of the air that is entering the engine, because that's a big factor too. The density of the air is going to change significantly with temperature. If it's 20 below or if it's 90 degrees, we're going to have to change our fuel delivery. So it's an important input, but keep in mind that intake air temperature sensor is quite often built into the mass airflow sensor. So it's really 2 sensors in one. You have 5 wires. The air intake temp sensor is just a thermistor, 2 wires, has a 5-volt reference, and then a ground. And then there'll be 3 other wires for the mass airflow sensor itself. Again, power, ground, signal, very easy to check to see, do I have my power, ground, and signal? But like I mentioned, there can be a 5-volt power source to some sensors as opposed to battery voltage, but just depends on the application. If we're looking on our scan tool, some of the mass airflow sensor data PIDs that we're going to see. If you're looking at like a GM sensor, which uses a digital square wave as an output, and these things are actually little control modules, and it sends a frequency on a pulsed 5-volt wire. It's going to measure that in hertz. So you may see hertz as a data PID, especially if you work on GMs. It's pretty common. They have a digital type output sensor. One of the most common, and you can always find this in global OBD2, is grams per second. And this is grams per second of air entering the engine. And we'll come back to why that's a useful data PID a little bit later, but we definitely want to be able to identify that, and you can always find it in global OBD2 data, which is helpful because it's quick, it's easy, you know it's going to be there. The other data PID you might see if it's an analog type sensor, which means it's just going to, instead of a digital square wave output, it's going to output a voltage continuously variable anywhere between 0 and 5 volts. And that's how a lot of these sensors are set up. So as the airflow increases, the voltage output on the signal wire increases closer to 5 volts. And that might be the other data PID that you see in the scan tool for a mass airflow sensor. All right, back to where this sensor is mounted on our air intake tube. One of the most important things to understand about a mass airflow sensor is that all of the air that enters the engine has to go past this sensor while the engine is operating for the air mass to be measured properly. Now, don't mistake what I'm saying. The sensor itself does not physically measure the entire air mass. So it's not coming into contact with every molecule of air that's entering the engine. But in its housing, where it's mounted in the tube that's going in the engine, all of the air that goes into the engine has to move past that point. And it's engineered that way so that the sensor is sampling a small amount of air that goes past, but based on the engine size and the size of the air inlet and the housing for the mass airflow sensor, it can be calculated off of a sample of that air what the entire air mass is. But if some air enters the engine in a different spot, let's say a vacuum leak, something like that, it won't be taken into that calculation, and we'll get more into how it's making that calculation in a little bit here. There are 2 common types of mass airflow sensor that we see. One is becoming more prominent on modern vehicles, has been for several years, but we still see both out there. The 2 types of mass airflow sensors are a hot wire style mass airflow sensor and a hot film. We'll talk about the hot wire first. The hot wire, if you take one of these sensors out and you look at it, you can actually see the sensing element. It's just a little resistor. And these things are pretty tiny, pretty fragile, so be careful with them if you're going to do some cleaning. But it is just a resistor that is placed in the airstream. The idea here is that inside this mass airflow sensor, and if you crack one of these things open, there's a little circuit board, there's a logic chip. It's like a little control module, really. But what this sensor is doing in a hot wire style sensor is it's actually sending current through this resistor. And there may be more than one resistor. In a lot of cases there's a cold and a hot wire. But to simplify this, and I am simplifying it because, heck, I don't build these things. I just know enough to fix them. It sends current through this resistor. And the goal of the sensor is to keep this resistor at a set temperature above ambient temperature. And that's generally somewhere in the neighborhood of about 400 degrees hotter than ambient temperature. So if it's 70 degrees out, it's going to keep that little guy at 470 degrees, approximately. And there may be some variances depending on what you're working on. But that's the idea. Let's keep this thing at a fixed temperature above ambient temperature. Now, this resistor, once again, is placed in the airstream, in the air that is going past that sensor to enter the engine. What happens is, as the air goes past this sensor, little tiny air molecules are actually going over the sensor, making contact with it. They remove heat energy from this little resistor that's in the airstream. And the more air molecules that pass this resistive element, the more heat energy is taken away. And the sensor, again, its little control module, has some circuitry that monitors this, and it will increase the current to that resistor to keep it at the temperature, even if there's more airflow, which removes more heat. And then the sensor is monitoring how much current does it take to keep this little guy hot enough. That is put into a calculation and says, okay, the air is this temperature, ambient air, and it took me this much current to keep this little resistor hot. That means X amount of air just went past this sensor. That's the amount of air that went into the engine, and it's going to send that signal, convert it somehow either to a digital or an analog signal, send it back to the PCM in order to say this is the air mass that's entering the engine. And that's, again, basically, simply put, how a mass airflow sensor is going to make its calculation, a hot wire style sensor. If you want to think about it this way, think about, standing outside in the cold. I live in Minnesota, so it gets nice and cold around here. Let's say it's 30 degrees out, I'm standing outside, and it's not too windy. The air is going to remove a little bit of heat from my skin. I'll be cold, but I'll probably be okay. Now, imagine standing outside on a 30-degree day and there's a 20-mile-an-hour wind moving past you. You're going to be a lot colder. The reason is there is a larger volume of air molecules moving past your skin, removing heat energy from your body. And the same thing happens to the resistor. You rev up the engine, more air is going to go past there, which means more heat's removed from that resistor, which means the sensor has to apply more current, which means its calculation is going to go up and say, hey, this engine is ingesting a larger volume of air. The PCM is going to take that airflow measurement and then add the correct amount of fuel. Now, the trouble we see with these hot wire style sensors, and this is very, very common, has been for a long time, as long as they've been out there, is that they are susceptible to getting dirty and sending a false signal to the PCM. Now, what I mean by dirty is this little resistive element that's in the airflow stream can actually get coated with what just sort of looks like dirt, dust, or debris. And if you want to think about it, it's like a little blanket. And if you use my analogy of standing outside, here's what happens to that mass airflow sensor. If it's 30 degrees outside, it's windy, you're standing outside with no shirt on, those air molecules moving past you are going to remove a lot of heat from your body. You're going to be really cold. Now imagine wrapping a thick wool blanket around yourself in the same scenario. You're not going to have as much heat removed. You're actually going to retain your heat and stay warm. Well, the same thing happens with this sensor, with the resistive element. When it gets coated with dirt and debris, it acts as a blanket, and the incoming air does not remove the same amount of heat energy that it would otherwise. Well, the sensor doesn't know that it's coated in dirt, and so it responds like it normally would, and it actually reports a lower air mass back to the PCM, which results in a lower amount of fuel added to what's actually going into the engine as far as air. Long story short, we get a lean condition out of that. And that can happen through all RPM ranges, any operating point of the engine. We're not getting enough fuel because that mass airflow sensor is dirty. So a lot of times these can just be cleaned, pull them out, take a look at them, be very gentle again, because these they're very fragile, they're very little petite sensors, so you can damage them pretty easily. But I've had a lot of success cleaning them, and if you have a lean condition, especially if it's across all RPM ranges, one of the things I'm looking at is to see if my mass airflow sensor is dirty. And we'll talk about a few other ways that we can confirm this, but we're looking for positive fuel trims there that might indicate hot wire style sensor that has become contaminated with some dirt or debris. Now, I should mention the air filter plays a big role in keeping that dirt and debris out, but heck, sometimes little bits of stuff get passed. Sometimes the air filters are old, maybe not installed properly. There's a number of reasons that we can have extra dirt and debris in there, but even on a system that has a properly installed air filter over time, you can get enough particles through to coat that mass airflow sensor. One area that I see a lot, especially on younger people's cars, is they like to use the K&N and the cone style air filters with the cold air intake. And they use this in conjunction with a system that uses a mass airflow, and it almost always results in a sensor that does not read properly. Especially with the K&N filters, they use an oil to clean the filter. The little fragments of oil will come through, and they'll actually contaminate the sensor. Sometimes to the point where you have to replace the sensor. Maybe you can clean it, but I never recommend going with the cone or the K&N style cold air intake, especially if you have a mass airflow sensor. My thoughts on it are, if the manufacturer could have gotten away with a simple cone filter and a simple tube coming off the intake, they would have done that instead of engineering these complex air boxes. It's a marketing thing as far as cold air intakes go. I'm sure there's probably some benefit at some level, but for your average everyday driver, it's a waste of money. And you might end up damaging your mass airflow sensor as well. So save your money for something else. The other type of mass airflow sensor is a hot film style sensor. Now, everything I described about a hot wire sensor, this one actually works very similar. It has resistive elements, it's using heat, using current to keep those at a certain temperature, it's using the airflow to remove heat from those resistors and measure how much air is going in there. The only difference is it has these resistive elements put onto a small diaphragm. It's just diaphragm with temperature-sensitive resistors that are implanted within it. And the other things that are different about this sensor, if you look at the sensor, the air actually enters the plastic housing the sensor in a serpentine pattern, and it samples a smaller amount of air that's going into the engine as compared to a hot wire sensor. And this is actually just speculation, but it has to do with my experience, what I've seen. You don't see as many of these sensors get dirty, and I think it has to do with how the airflow enters the sensor. It's less likely that particles of dirt and debris are going to enter this sensor. Now, that's not to say they can't fail, they do, but here's what I've noticed with these hot film style sensors. And if you were wondering, do I have a hot film sensor or not, pull it out and look. If you can't see one of those resistors, if it's not visible, it's most likely a hot film style. I have not had luck cleaning these, and my guess is they probably don't get as dirty. Once these things fail, I've had to replace them if they're not reading correctly. As opposed to a hot wire, I've had pretty good luck cleaning them. So you kind of have to take it case by case, but again, I've not had good luck cleaning these hot film style sensors. From what I have read on the hot film style, they are slightly more accurate. They can make up for turbulence in the air intake. You can have pulsations back out from the intake depending on the conditions of the engine, and they can compensate for that. And just the fact that I think they're more resistant to getting dirty. So that might be an advantage to one of these sensors. And you see a lot of manufacturers going this route. Most of the new mass airflow sensors I've seen have been the hot film style. So those are our two types of sensors that we're talking about. Again, the goal of them is the same. Let's measure the air mass going into the engine. That's really it. So when we're diagnosing these sensors, we can keep in mind what we're working on, but again, the goal is the same. A lot of time the output on the signal wire will be the same, either digital or analog, but very, very similar in ultimate goal, slightly different in how they measure the air mass. All right, now back to an important point about any mass airflow sensor. Covers any one of them. All of the air that enters the engine while it's running needs to go past these sensors. Okay, so if we have air entering the engine anywhere else than through this mass airflow sensor housing, it is not going to be added into the calculation, and we will not add the proper amount of fuel. So the question is, where else could air enter the engine? Well, there's a number of places that this could happen. Obviously, vacuum leaks of any type, intake manifold gaskets, manifolds that are cracked or damaged, injector seals on a multi-port injection style. You could have any component that runs off of vacuum under the hood. Let's say a solenoid. Let's say a brake booster. Anything that runs off a vacuum, a hose that's torn, a line that's cracked, an O-ring that's broken, that is going to be a place where atmospheric pressure, because if you think about a running engine at idle, throttle's closed, we want all that air to enter through the throttle. That's the goal. And when it's closed, there's a small amount of air that's going in, so the engine can idle, or maybe pass the idle air control valve if it has one. But there's atmospheric pressure trying to get into this intake manifold, because as the engine's running, we have intake strokes, we're creating a negative pressure or a vacuum inside that manifold, and all of the air, the 14.7 psi around us, atmospheric pressure, is trying to equalize itself. It's trying to push its way into this intake manifold. And if everything's sealed up properly, the only way that it can enter in is through the throttle, which means it'll get measured by the mass airflow sensor. But if we have a vacuum leak of some sort, again, we have a cracked vacuum line, or if we have a intake manifold gasket or a solenoid that's stuck open for something, atmospheric pressure will find its way in because it's surrounding everything around us. Well, as we stand on the earth, we have 14.7 psi of absolute pressure pushing in on us in all directions. It's going to find its way through, even on the smallest crack. So if it does, that air gets in there, it goes into the engine, it's part of that intake stroke, but if the mass airflow sensor didn't measure it, the computer doesn't know about that air, and it does not add the correct amount of fuel. So that's what we run into. That is a vacuum leak, and we'll describe exactly how that's going to present itself in a mass airflow sensor situation. So if we think about our injector pulse width, and if we have a given amount of fuel, let's just say let's go with our stoichiometric mixture, 14.7 to 1. So the 1's going to be fuel, and our 14.7 is going to be air. That's a ratio. Now, it's not all oxygen. It's oxygen, nitrogen, and inert gases. But we have our 14.7. Let's make this easy. 14.7 grams of air entering the engine at any given point, okay? That's our stoichiometric mixture, but we're just making the math easy here. The engine computer is going to add 1 gram of fuel for that 14.7 grams of air that entering the engine, because all of that air went past the mass airflow sensor. It sent a signal to PCM. PCM added 1 gram of fuel. Easy. Everything worked out great. Engine's running perfectly. Fuel trims are right on the money. But let's say we have a vacuum leak, and a little bit of air enters through a vacuum leak into this engine. And now there's still air going past the mass airflow sensor, but that air volume is going to be reduced. So now, let's say our air volume reads 13 grams instead of our 14.7 to 1. But with that vacuum leak, if you take that into the equation, and again, I'm making the math really easy here, it's actually 14.7 grams of air. If you include the vacuum leak, the torn vacuum hose, and what air is going in through the throttle, it's still 14.7, but the mass airflow sensor only saw 13. So it reports 13 to the engine computer, and the engine computer only adds fuel for 13 grams of air, which is 0.88 grams if you care. But now what we have is 14.7 grams of air really entering the engine, and the engine computer only adding 0.88 grams of fuel. So what do we get? We get a very lean mixture from that. More oxygen than we want, less hydrocarbons than we want. We have a lean mixture. Now, where does this get picked up in engine operation? The oxygen sensor, if it's in closed loop, will pick this up and say, hey, you did not add enough fuel, or some reason or another there's too much air going into this mixture. So the computer responds with its fuel trims, adjusts the fuel map. It's going to go positive and add more fuel to that injector pulse width to try to compensate. And depending on the size of the vacuum leak, it will compensate to a certain point, and then it will stay flat, or it will go as high as it can and then set a fuel trim code because it realizes I can't add enough fuel. Something is wrong here with the calculation. So anything that's going to allow air to enter the engine that the mass airflow sensor does not see is going to be presented as a lean condition, and it is going to increase fuel trims in a positive direction. That's a vacuum leak on a mass airflow sensor. Now, there's another way that we can get unwanted air into this calculation, and this is commonly known as false air. Now, what false air is, remember I said the mass airflow sensor is in the air duct before the throttle, okay? And all of the air that goes in the engine has to go past that sensor. Now, we can have a leak in that air duct itself between the mass airflow and the throttle, okay? So this is, think about the flow through here. We go air filter, mass airflow sensor, air duct, it's like a rubber tubing most of the time, and then the throttle plate. I'm talking about a leak somewhere between that mass airflow sensor and the throttle plate. Maybe it's a torn hose, maybe it's a tube that was pulled out, maybe a clamp wasn't tightened down properly. Air can actually enter the engine there. Now, this isn't technically a vacuum leak, although it will present itself very similar to a vacuum leak, but not exactly. And we'll get into the testing methods and how we identify vacuum leaks in each of these systems. And false air doesn't necessarily present itself exactly like a vacuum leak. But this can cause very similar symptoms to a vacuum leak because, again, air is entering the engine somewhere else than through that mass airflow sensor housing. And that's really what the key of that is. All right, if we look at these mass airflow sensors, one other key point that I want to make is it's very important how the air enters the sensor. Not only that it measures all of the air goes past it, but how the air goes past this sensor. Again, they're sensitive to turbulence. They can actually put out the wrong voltage or a erratic voltage if there's a lot of turbulence going into these sensors. So there's a couple things that you need to note here about sensors. And take a look if you're getting weird mass airflow sensor readings. These are something that you want to check. Number one, there's a screen in front of a lot of these sensors. Sometimes it looks like a honeycomb, sometimes it's a metal mesh. There's variations of it, but in a lot of cases, there's a screen. The idea of this screen, the purpose of this screen is to straighten the air going past that sensor so there's not a lot of turbulence. So the key here is don't damage or remove this screen. It will cause problems to the mass airflow. You need this screen there so that it reads properly. The other part of this is the air filter housing itself. If the mass airflow sensor is very close to the air filter housing, which a lot of them are, the air filter and the housing itself can make a big difference in the way that that sensor reads the incoming air. If you're missing an air filter, if you have the wrong air filter, if the air filter is not installed correctly, if the housing is damaged, any of these things, even a mouse nest inside the air filter housing, I've seen this, can disrupt how the air goes past that sensor. Not necessarily that a different amount goes by, but how it goes past this sensor. The amount of turbulence can affect the readings of the sensor. So that is something that you need to take note of when you're looking at mass airflow sensors and saying, is this reading correctly? Take a look at that air filter housing. Take a look at that screen in front of it. Make sure that everything is in place and factory set up. That's very important. And another reason I don't really suggest the aftermarket cold air intake setups with a mass airflow system. So one of the biggest challenges we have with mass airflow sensors is how do we tell if this sensor is reading the correct amount of air? It's what makes a mass airflow sensor one of the more challenging sensors to diagnose compared to other sensors. I'm going to give you some methods here, but I want you to consider something here. If we had a coolant temperature sensor that we, for whatever reason, thought was skewed, okay? Because, if a mass airflow sensor is completely out, if it's reading 200 grams per second and the engine's not running, that's a problem. If it's reading 0 grams of air per second and the engine is running, we have a problem. But what often happens is it's just slightly skewed. And we want to know, is that number correct? Is this thing off? Because even a slight amount of variance in the sensor can really throw off the fuel delivery and the fuel trims for an engine. But back to what I was going to get with here. Let's say we had a coolant temperature sensor that we thought was slightly skewed. It was 20 degrees off. We had that suspicion based on some symptoms that we were having. It's pretty easy to check to verify if that sensor is actually reading the correct temperature. We just physically measure the temperature of the engine or the coolant, okay? Use an infrared temp gun or use a thermal imager or put your hand on the thermostat housing. You can verify that sensor. Let's say we had a MAP. Okay, this is a manifold absolute pressure sensor, measures the pressure in the intake manifold. We thought that was reading incorrectly. Okay, put a vacuum gauge on the intake manifold and see, does this number correlate with what the sensor is putting out? We have an oil pressure sensor, and that we're considering that this oil pressure sensor may not be giving us the correct number. What do? Put a mechanical gauge on there and check the oil pressure. We have an air intake temperature sensor that we don't think is reading correctly. What do? Look at the temperature outside. We have a throttle position sensor that's not reading correctly, or we think it's not reading correctly. How do we verify? Look at the throttle. Is it at the percentage opening that the sensor says it is? Okay, so you get my point here. A lot of sensors in vehicles, not all of them, but a lot of sensors, if we are suspecting that they are skewed or not reading correctly, we have a way to verify what that sensor is measuring with some sort of test or visual aspect. The mass airflow sensor is not one of those sensors. And this is what makes it difficult to diagnose, is that we don't have an easy way. I'm sure it's possible, but I don't have an easy way to measure the incoming air mass into an engine. Okay, so if that sensor, let me give you an example. If that sensor says there's 5 grams of air entering this engine per second, I have to take the sensor's word for it because I don't have a device that I can just slap on an engine to tell me how many grams of air per second are going into this engine. I don't know. There's not an easy, quick way to verify if that sensor is measuring the correct amount of air mass. There are ways to test a sensor. We're going to go through a few of them here. One of the common ways that's been used over the years, and I'll give a warning up front about this, that this is not always accurate and there are variables, but it's one quick check that I will usually make. Here's what you do. Take the engine size in liters, okay? So my Buick that I drive around has a 3.8 liter engine. So 3.8 is the number that I'm going to use. You get the idea there. Now, on a warmed up engine, idling, in gear, okay, so I got it in driver reverse, my engine is at operating temperature, I am at idle, I'm not revving this up, and we look at the grams per second from the mass airflow sensor, it should be somewhere in the neighborhood close to my engine size. All right, so let me give you an example. My 3.8 liter engine should be somewhere in the neighborhood of 3.8 grams per second at that given point. Now, it's not going to be perfect, but it should be close. It should be somewhere I would want to see it anywhere from, 3.5 to 4.5, somewhere in that neighborhood. Now, if I start getting to 5, 6, 7 grams per second, or much lower than that, 2.5 grams per second, I'm going to consider that maybe that sensor is not reading correctly. Now, here's the deal with this. Again, you have to have the engine in the right condition. If you do this cold, your engine's going to be ingesting a lot more air. That's going to make a big difference. The other part of this is this does not work well on engines that are below 3 liters of displacement, which we have a lot of those engines nowadays. A lot of smaller 4-cylinders that don't apply themselves to this rule. You can have Kias and Hyundais that are significantly higher in air volume than what their actual engine size is. So you can use this as a quick check, but don't rely on it completely. It is not 100% foolproof. So anything under 3 liters of displacement, I don't use it. And even on engines above 3 liters of displacement, I take this with a grain of salt. But generally speaking, grams of air per second entering the engine should equal the engine size on a warmed up vehicle idling in gear. So that's one way we can check this sensor to see, is it in the right neighborhood? All right, another test I've seen done over the years, which, again, not saying this can't work, but I don't really like relying on it, is unplugging the sensor and seeing if your fuel trims go back to normal or whatever performance condition you were suspecting goes back to normal. Here's the problem. You don't always know what the computer strategy is going to be once you unplug that sensor. And it may go into some sort of default mode that makes you think that you corrected the problem by unplugging the sensor, but you didn't really. Here's another thing, too. If you have a mass airflow sensor vehicle with a vacuum leak, the fuel trims are responding positive because of the mass airflow sensor. It's measuring air volume. I explained that whole process. Now, let's say I unplug that sensor. Is the engine computer going to be able to identify that it has a vacuum leak? It's probably not. So unplugging that could correct your fuel trims to a point, but replacing that sensor is not going to fix the problem. You need to find the vacuum leak. So I don't rely on unplugging the sensor in order to verify if it's reading correctly or not. Now, once again, it's not 100% of the case that you can't use this test. And let me give you an example. I had an Impala not that long ago that had a mass airflow sensor that was all of a sudden spitting out 200 grams per second randomly when I was at an idle, and it would stall the engine. So I unplugged the sensor and I was able to drive the vehicle just fine, and it stopped doing that. So that's more in the case of a sensor that's failed completely, but be careful with this test method. It's sketchy at best, I would say, unplugging the sensor to see if your problem or your fuel trims go back to normal. Not my favorite way to test a sensor. If those methods don't work for testing a mass airflow sensor, what else can we do? And again, this is a sensor that's slightly skewed, not one that's completely failed, one that we think is just reading a little bit off of where it's supposed to. How do we verify that? Where do we go with this? And that's where I'm going to leave you with today. And what we're going to talk about in our next episode is something called volumetric efficiency testing. Now, we can use this testing for a few other things, but one of my favorite uses for a VE test is determining how accurate our mass airflow sensor is. And I think it's one of our best shots to gauge, is this mass airflow sensor skewed or not? At least it's going to give us a pretty good idea of where this thing is reading. So with that, I'm going to leave you today. Thank you for tuning in, and we hope to see you again